Our next speaker is Taeyong Choi, data scientist at Condé Nast. In his talk about content personalization, he will cover how the recommendation system at Condé Nast learns various entity latent vectors that are both easily interpretable and can capture multiple user interests. Take it away, Taeyong.
Hi, everyone. Thank you for joining my talk. My name is Taeyong, and I joined Condé Nast as a data scientist in 2019 and have been involved in multiple data science projects, such as recommendation systems, consumer segmentation, ad targeting, forecasting, and churn modeling. But I personally found that building a recommendation system was the most challenging task, but at the same time, it has been the project that I enjoyed the most. I'm currently leading the recommendations teams at Condé Nast, and our team is in charge of multiple personalization initiatives, from personalized newsletters to on-site recommendations. And today, I'll be talking about how we built our recommendation system using an embedder framework. Here is today's agenda. First, I'll give a brief introduction to Condé Nast and explain the unique challenges we face as data scientists. Then we'll go over the embedder framework that powers Condé Nast recommendation system, and I'll walk you through one of the use cases of it, which is newsletter personalization. Condé Nast is an American mass media company founded in 1909. Condé Nast is home to some of the world's most iconic brands, such as The New Yorker, GQ, Vogue, Wired, and many more, as you can see on the screen. We are operating in 32 different markets globally and publish in 26 different languages, with more than 75 million monthly print readers and 363 million monthly web page views. Now, let's try to narrow the scope down to our readers and contents in the United States and look at their digital scales. Across all US brands, there are more than 8 million daily unique visitors, and 160,000 of them are logged in subscribers, which is roughly 20% of the total daily visits. This is a lot of users, and here is the first problem that we face. 80% of the visitors are non-subscribers, and we would like to somehow encourage them to subscribe. However, there's a very limited number of actions that we can take, as we don't have much data about them, and they tend to have very short session length. At the same time, we value our subscribers, and we would like to provide them with good subscription experiences so that they could remain as our subscribers. Here's the other side of the business, our contents. We publish more than 100,000 new or revised articles every month. I'll take The New Yorker as an example. The New Yorker publishes a mix of reporting on a wide range of topics, including politics, culture, humor, cartoon, fiction, and book reviews. If we include other brands as well, the list goes on and on. Just like so many different readers that we are serving, we are producing a broad spectrum of contents. And here's a constraint that we see with our contents. Many of them tend to have relatively small lifespans, as editorial teams will often revise them with up-to-date information and connections to new cover stories. As a result, on average, 48% of traffic is made within the first 24 hours after publishing, and 2/3 of the traffic is made within the first 48 hours. So we have to act fast while these articles are still relevant to many readers. So we have laid groundwork for our problem. Let me reiterate key features of our readers and contents. We have more than 8 million daily unique visitors, most of them being first-time visitors. We publish more than 100,000 articles every month on all sorts of different topics, and they have short lifespans. We want to show our readers relevant contents that they'd like to read so that we encourage new visitors to subscribe and improve subscription satisfaction for our subscribers. This type of problem is exactly what a recommendation system can effectively address. Objective of a recommendation system is to provide recommendations based on recorded information on the user's preferences. A good recommendation system can help us gain complex insights into our readers and contents. It can also increase brand loyalty and satisfaction. In addition, it keeps our readers interested and it can improve brand health as well. A recommendation system can bring tremendous values and opportunities to a business, but doing it right is very hard. And that's why I spend time explaining about our readers and contents. So at Condé Nast, we need a recommendation system that knows how to deal with cold start users and cold start items. This is where many of the traditional matrix factorization-based recommendation system could fail. By the time we collect enough data to perform matrix factorization, many articles would become stale and we cannot use them in recommendations. And we would have no clue on how to recommend new articles. Also, it has to be scalable. We are operating at scale and predictions must be efficient. This is why we need an embedding framework that transforms readers, articles, and user features into embeddings and use them to generate recommendations. Many of you might be familiar with word-to-vec already. Word-to-vec is a method to efficiently create vector representations of words that carry semantic meanings. I won't be getting into the details of it today, but I'll go over the high-level idea of word-to-vec because the embedder framework we built at Condé Nast is a variant of word-to-vec. Consider a one-word context setting where the model predicts one context word given one target word. For a word pair, IJ, I being the target word and J being the context word, the likelihood of seeing the pair together is represented by the dot product between the ith row of the embedding matrix you see on the slide and the jth column of the context matrix. Because the objective function of word-to-vec is to maximize the dot product between the vectors of frequently occurring word context pairs and minimize it for randomly chosen pairs, that got us thinking that if we treat readers as target words and context words as articles, we can find user article pairs that are more likely to be seen together in the learned embedding space. Here is the revised version of the previous diagram. We see the user matrix on the left and article matrix on the right. In the original setting, both target words and context words are part of the same vocabulary. However, we are going to separate users and articles and treat them differently. So the inputs are the users and the outputs are articles. As you can see in the slide, word embeddings and context embeddings are learned simultaneously in the original setting, and the context word embeddings are discarded in applications. In this case, in our case, if you discard the article matrix, you would know how to represent our readers, but we would not know how to represent our articles. But that's okay, and here's why. At Condé Nast, we have a real-time content intelligence API called HOW, and it is running a fine-tuned text-to-vec service that generates vectors for any arbitrary sequence of text. This is the key feature that we can overcome the cold start problem, and the reason why we are separating users from articles in the previous slide. As you can see, the articles that have similar content live in a neighboring subspace of the article embedding space. So coming back to the word-to-vec diagram, we will be constructing the context matrix using the article embedding produced by HOW. During training, we won't be learning both matrices simultaneously. Instead, we are going to fix the context matrix and update the user matrix only. The intuition is that user vector is constructed through the lens of the article embeddings, and user embedding will seem much like article embeddings after training. Some of you might think that it is just a weighted average of article embeddings that a reader has interacted with in the past. And that observation is totally valid. And we are only halfway there, but it seems like we've already solved some problems that we've stated in the beginning. We are using article embeddings from our NLP service and use them to build user embeddings. They are of the same dimensions, so whenever we see a new article, each article embeddings will be available right away. And we can compare that against the user embedding to calculate the likelihood of a user reading the new article. The operator that calculates the scores is just a simple dot product. So it is very cheap computation, so it's very scalable. Also, if we represent our readers through the lens of articles, the user representations are interpretable. For example, pulling the closed article embeddings to a user embedding will define what kind of reader this person is to us. This is very valuable to us in terms of understanding our readers and how they are interacting with our content. As I mentioned, we've only come halfway to the final solution. There are remaining problems to solve. The model is intrinsically linear, and to be precise, it is log linear model. Therefore, we cannot embed complex information into our user embedding. We will visit the counterexamples that previous models will fail. Also, we still don't know how to deal with new users yet, which accounts for 80% of our traffic. Here's the first example. Assume you've visited the New Yorker on March 15th, and these are the articles that you will find on the website. Articles about 2021 Oscar nominations, universal basic income, behind the scene at 5-star hotel, and COVID-19 vaccines. If you click through all of them, then what will be the resulting user embedding look like? Where would the weighted average of these article embeddings point at? It might be pointing at the articles related to the sports or fiction articles. You never know. The takeaway from this example is that if you are an explorer and have multiple interests, the current approach might not be the good solution. But at the same time, it could work well for the people who knows what they want and repeatedly visit the same section of the website. How about this example? Can you find something that connects these articles together? The parenthesis represents the sections of the New Yorker magazine. These articles are writing pieces about pop music, Mike Tyson, also filmmaking. The answer is that they are all written by the same author. If we use the previous approach again, we would have missed the opportunity to recommend his articles to his fans. Especially for the New Yorker, our readers tend to follow celebrity authors and read content pieces. So this kind of relationship is a very important factor in how our readers are interacting with content, and it is our data scientists' responsibility to reveal them and incorporate it into our model. Luckily, we have a solution. This is where we need to introduce nonlinearity into our model. Instead of learning a single embedding for a user, we can learn multiple embeddings that capture multiple user interests. The idea was inspired by the paper named Nonlinear Latent Factorization by Embedding Multiple User Interests. You will be able to find the link in the slide. This is a slightly different representation of the model, but the input is the same. We have a user article pair, and we have a metadata table which stores article embeddings from how. In the previous model, we had a single user embedding matrix, but here we have k different embedding matrices. K is the model hyperparameter that you choose, and it decides how many different interests you want to learn for a user. All k embeddings become candidates, and we will take pairwise dot products between article embeddings and user embeddings. This will end up with k different values, and we can take the maximum of these k different values, and the user embedding that produced the maximum dot product will get selected and used throughout the training for this specific input pair. In words, say you read a politics article and your politics interests will get updated. If you read another politics article, your politics interest will get selected and get updated again. If you read a culture article, it is very unlikely that your politics interest will get picked and updated. Rather, one of your other embeddings will get selected and record your new interests about culture articles. As a result, if you read politics and culture articles together, the model can learn two separate user embeddings. Each of them covers one of the politics and culture article embedding subspaces. We are not restricted to constructing user embeddings. We can build embeddings for demographic features, authors, popularity, devices, geolocation as well. We can simply substitute users with entities that we want to learn embeddings for. So we can deploy recommendation strategies like what New York City is reading, authors you might also like, people like you are reading. Also, the fact that we can find similar users to the first-time users based on geolocation and device and use relevant embeddings to personalize, we can solve the cold start user problem. Ultimately, these various entity embeddings together provide complex insights into our readers and contents and allow us to produce robust recommendations. Lastly, we'll look at a use case of the recommendation system that we built. So we have launched personalized newsletters on these three different brands, The New Yorker, Vanity Fair, and Wired in 2020. Before we launched this product, we've conducted A/B tests against our email vendor personalization solutions and proved that the in-house recommendation system was significantly better. So we decided to deploy to production, and we are preparing additional launches for other brands as well. So with the personalized newsletters, we were seeing 10.5% more page views per user and 6.7% more monthly visitors. These positive engagements from readers also led to a higher subscription retentions as well. Thank you for tuning in, and I'll take any questions.
Awesome. Thank you, Taeyang. Looks like you guys are doing some amazing things over at Condé Nast. We do have some wonderful questions from the audience. Let's start with, what kind of tools do you use for your framework?
So we are using Databricks to manage our clusters and pre-process large data sets using Spark. It also has a native support for writing out data into the TF records format. It also supports distributed GPU training for TensorFlow. So I find using TensorFlow very convenient given the technical environments that we have at Condé. And we also have different opinions about which packages to use to build models internally. But the recommendation model that I just used is building using TensorFlow 2.0 with multi-machine distributed training for scalability. And then we write the trained embeddings out to Delta Lake, which then gets passed to downstream applications. Yeah, that's the high-level architecture of the framework.
Awesome. And what are the areas that you can further improve in your model?
So even though the training processes are nonlinear, the prediction process is quite simple. We compare user embeddings against article embeddings to compute the scores. We just use the dot product for that. As I mentioned, we have demo embeddings and author embeddings as well. We also compute scores separately and add them all together in the end at the prediction phase. And we think that if instead we train a neural net on top of these embeddings to capture more complex information and improve the recommendation qualities. We are also looking into different methods and architectures that builds embeddings, such as graph neural nets and the encoder-decoder approach that takes in article and user metadata pieces into the model. So we are exploring different methods, and this is still work in progress. But yeah, this was the model that was deployed to the production first, and we'll trying to improve this model.
Very interesting. Thank you for sharing. We've got time for one more.
Sure.
What advantages does the multiple embeddings method have over other recommendation system approaches that can incorporate different types of data and solve the cold start user problem like alternative least squares?
for example, like alternative least squares, that requires constructing a fixed matrix, and everything that we can do about recommending articles or items to a user is that happens within this fixed matrix. For example, as I mentioned, the problem with the Condé Nast articles is that they have very short lifespans. So by the time we train the model, and here are the items that we use to train the model will not be available after we train them, because that article is not relevant anymore. So in order to infer the likelihood of a user seeing an item, even if this is the first time that we are seeing this article, I have a lot of difficulties to solve that problem. That's why we try this approach by constructing user embeddings, just like article embeddings that we can directly compare them at a relatively cheap cost. And also we can also embed different, because article embedding itself embeds a lot of different information already, so that there's no like additional work that to be done in terms of like incorporating complex information into author embedding. So half of the work was already done. We were using that to represent our readers as well, and we find it very efficient and it was working quite well.
Well, thank you so much again, Taya, for joining us today. Your information has been very insightful, and we appreciate everything. For those of us who are joining us, please pop over to our final event of the day. Amit from Vox Media will be joining us to talk about content-driven advertising using first-party data. We will see you there.